Hello and welcome to the next in this series of videos about noise in electronic circuits. This time we're going to look at noise in op-amps. Now, we haven't seen inside an op-amp before, but a typical op-amp looks like this if you plotted its circuit diagram. Now, remember that every diode and every transistor has a shot noise component associated with it, and every resistor will have a thermal or Johnson noise component associated with it. So in this op-amp, there are over 30 different independent sources of noise. It would be an extremely difficult calculation if we were to consider all of them whenever we wanted to determine the noise in an op-amp circuit. So we don't. We use a simplified noise model of the operational amplifier, something that looks like this. We've just got three noise sources here. Two noise currents, one on each of the two inputs to the op-amp, and one noise voltage. They're called equivalent input noise sources, since they are equivalent to the entire noise contributed by all of those 30 plus noise contributions of the amplifier. This amplifier here, with these three noise sources, coupled with an entirely noiseless op-amp, behaves exactly the same way as this full noisy op-amp circuit here. And the values of these noise currents and noise voltages, which are usually expressed in volts per root hertz and amps per root hertz, are given in the datasheets of the operational amplifiers. It's worth pointing out that just because this is an equivalent input noise current doesn't mean that the only contributions to this come from the noise currents in the semiconductor devices, the shot noise. Similarly, the noise voltage there doesn't just correspond to the noise voltages in the resistors, the thermal Johnson noise coming from the resistors. Those three noise sources together represent all of the noise from all of the noise sources in the op-amp. But a lot of the shot noise contributions from these transistors actually correspond to an element in the noise voltage there, the equivalent input noise voltage. Now, as the manufacturer of the op-amp doesn't know what bandwidth is going to be of interest to the designer, they specify the noise in terms of volts per root hertz and amps per root hertz. All the designer has to do is then to take those figures, multiply by the bandwidth of their circuit, and they will get an estimate for the total equivalent input noise contributed by the op-amp. For example, consider an extract from the TL071 datasheet. The equivalent input noise voltage is specified with a source resistance of 20 ohms, like this. At 1 kHz, it's 18 nanovolts per root hertz, and it's also specified as a sum of all of the contributions from the frequencies between 10 Hz and 10 kHz as 4 microvolts. The equivalent input noise current, remember there are two of them, that is specified at 1 kHz as 0.01 picoamps per root hertz, again with a source impedance of 20 ohms. Okay, now a few questions might occur to you when you look at those figures. Firstly, why is RS, the source resistance, so low at 20 ohms? That is far smaller than any resistor that we're likely to use in an application circuit. And the reason is because that resistor then contributes negligible noise. You might remember that the RMS noise voltage contributed by a resistor is given by 4kTBR. So if R is very small, then the noise voltage contributed by that resistor is very small as well. And that means that most of the noise at the output of the amplifier will be due to the amplifier's noise, and not just an amplified version of the noise provided at its input. Why then, you might ask, don't they use a source resistance of 0? Then there would be no input noise at all. Well, think about it for a minute. Supposing you did build a amplifier, and this resistance here, that's the source resistance RS, that was set to 0. Well, there would be presumably quite a large resistor there in order to give the amplifier quite a bit of gain, maybe, I don't know, 2K or something like that. So with 20 ohms it has a gain of 100. That would allow you to have a reasonably large voltage at the output, which would be possible to measure. At least if that was 20 ohms, we've got a gain of 100. Any noise contribution from the equivalent input noise of the amplifier would be multiplied up by 100. It would be measurable. But if that is 0, then the gain of our amplifier is infinite. That's not going to work very well. The amplifier output is going to be saturating all the time, and it wouldn't give a sensible reading of the noise. So we need a small but finite value, small enough so that it contributes much less noise than the amplifier contributes itself, so we can neglect the Johnson thermal noise contributed by this resistor, but big enough so that we can get a reasonable amount of gain from the op-amp circuit, so we get a signal out here big enough to measure accurately. Next question. The total noise from 10 Hz to 10 kHz is specified as 4 microvolts, but 10 Hz to 10 kHz is a bandwidth of 9,990 Hz. If you take 18 nanovolts and multiply it by the square root of 9,990 Hz in order to calculate what the total output noise would expected to be between 10 Hz and 10 kHz, then the answer that you get is 1.8 microvolts. But the datasheet says 4 microvolts. What's wrong? Well, what's wrong is that the noise that we're getting from the op-amp is not white. This is an excerpt from the datasheet, a graph provided, and you'll see that whereas above 10 kHz, the noise is effectively independent of frequency. But below 10 kHz, and certainly below 1 kHz, the noise is not independent of frequency. We have quite a lot of 1 over f noise which has a lot more power at low frequencies. So we can't just take the noise in nanovolts per root hertz, multiply that by the square root of the bandwidth, and expect to get the total noise, because that formula assumes that the noise is white. And it isn't. We've got more power than that at these low frequencies. And that's what that specification tells you. The total noise from 10 Hz to 10 kHz. Right. So, why specify it from 10 Hz to 10 kHz and not from 0 to 10 kHz? The answer is it's quite difficult to measure noise below 10 Hz. You'd have to measure it for quite a long amount of time to get an accurate measurement. And a lot of applications aren't interested in very, very low frequency noise. If you have an application that really does need an extremely small amount of noise at very low frequencies, then a TL071 is probably not the op-amp that you would be using anyway. There are some op-amps and some whole families of op-amps that are designed for very, very low noise operation at very low frequencies. This isn't one of them. Finally, is voltage or current noise more serious? Well, it slightly depends on the application, but with a voltage noise of 18 nanovolts and a current noise of 0.01 picoamps, both per root hertz, it's much more likely that the voltage noise is going to cause you a problem in most applications. but we can calculate both of their effects in a typical amplifier, and we'll be doing that in the next video, just to see how big the effects of these two noise voltages are. Another point I'll make just while we're here is that there's no point in measuring noise at DC, at 0 Hz, because there's no such thing. Noise at 0 Hz would just be a voltage offset, which doesn't change. It's at 0 Hz. It doesn't move. If there's just a fixed offset, then we can compensate it out, so it's not a problem. Okay, that's the end of this one. Next time, as I mentioned, we're going to have a look at the noise in a real amplifier based on an op-amp and see which ones of these contributions are actually the most significant in a real circuit.